survey help engineers select materials and plan construction to prevent future failures like cracks and deformation. The primary goals of soil survey are to investigate soil characteristics and identify suitable materials for subbase and fill layers. Geophysical method of soil exploration. To gather this data, geophysical methods are often employed. Resistivity method. This technique measures how well soil conducts electricity. Different types of soil have unique electrical resistivity properties, making this a useful tool for identifying soil layers. Seismic method. This approach measures how sound waves travel through the ground. It is particularly effective at locating rock layers or dense strata beneath softer soils, which is essential for assessing stability. Both methods provide valuable insights that help engineers design a stable and reliable road structure. The next step is soil compaction. Why is compaction important? It's to ensure that the soil can support the weight of the pavement and traffic without settling or shifting over time. The process involves placing the soil in uniform layers and compacting it to achieve high density. Without proper compaction, roads can fail prematurely due to uneven settlement or water infiltration. Now let's move to soil tests that guide pavement design. These tests provide the data need to make decisions about material strength and stability. California Bearing Ratio or CBR test. This measures the soil ability to support loads. It's especially useful for evaluating the strength of the subgrade. The stabilimeter test. This assesses the stability of material under load, helping engineers select the right material for the pavement layers. Each test plays a role in designing a pavement structure that can withstand traffic demands. Next, we have the types of pavements. There are two broad categories: flexible pavements and rigid pavements. Flexible pavements are called so because they flex under load and transfer stresses through grain-to-grain contact within the material. Let's look at the three main types of flexible pavements. Conventional layered flexible pavement. This system uses high-quality durable materials for the top layers, where stresses are highest. Lower layer use more economical material. Full depth asphalt pavement. This involves placing bituminous layer directly on the soil subgrade. It's ideal for regions with heavy traffic or where high quality materials are unavailable locally. Constrained rock asphalt mat. This innovative design sandwiches dense or open graded aggregates layer between asphalt layers. It reduces vertical compressive strain on the subgrade and offers excellent protection against surface water damage. On the other hand, rigid pavements are made of concrete and distribute loads over a wider area, reducing the pressure on the subgrade.
Good day, everyone. Today, I'm going to discuss the typical layers of flexible pavements and the roles of seal coat, tack coat, and prime coat in pavement construction. So let's dive right in. So first is we have seal coat. So seal coat, this is a thin layer of bituminous material applied it to the surface. Its purpose is to protect the pavement from water infiltration, oxidation, and wear. It also improves the skin resistance, making the surface safer for vehicles. Next is tack coat. So a tack coat is a thin application of bituminous material placed between pavements layers. So the job of tack coat is to create a strong bond between layers, preventing them from separating under traffic. And next is prime coat. Prime coat is applied to the granular sub-base or base layer before placing the surface course. It penetrates the base to bind loose particles, provides a dust-free surface, and ensures better adhesion with the layer above. Now, let's talk about the typical layers of flexible pavements, which is the surface course, the base course, sub-base course, and the last one is subgrade. Now, here, the surface course, this is the topmost layer made of high-quality asphalt or bituminous material. It provides a smooth, durable surface for vehicles, resists wear and weather effects, and ensures skid resistance. Next is base course. So below the surface is the base course, typically made of crushed stone or stabilized materials. So the job of base course is basically to distribute the loads evenly and provide structural strength. Next is ang sub-base course. So this is the layer that acts as a secondary support, often made of lower quality materials like gravel or crushed stone. It also helps with load distribution and serves as a drainage layer to prevent water accumulation. And the last one is subgrade. So prime coat is applied to the granular subbase or base layer before placing the surface course. So prime coat, it penetrates the base to bind loose particles or provides a dust-free surface and ensures better adhesion with the layer above. So of course, these treatments may seem minor, but they play a crucial role in extending the pavement's lifespan and ensuring its performance under traffic loads. So now let's proceed the failure of flexible pavements. So the major flexible pavement failures are fatigue cracking, rotting, and thermal cracking. So the fatigue cracking of flexible pavement is due to horizontal tensile strain at the bottom of the asphaltic concrete. So here, and the failure of flexible pavement, we have rigid pavements. So rigid pavements have sufficient flexural strength to transmit the wheel load stresses to a wider area below. So, as we all know that rigid pavements used in construction, right? So rigid pavements are called rigid because they are made of strong, stiff materials like concrete. Now, let's explore the main types of what makes each unique. Rigid pavements are primarily made of Portland cement, concrete, or PCC. Which provides a high level of strength and durability, unlike flexible pavements. Rigid pavements distribute loads over a wider area, reducing stress on the subgrade. So now, I'll explain the four types of rigid pavements, which are essential in modern road construction. So, the four main types are, first is jointed plain concrete pavements or GPCP. So, the first type of jointed plain concrete pavement or GPCP uses regularly spaced joints to control cracking due to temperature changes and shrinkage. So, it does not include any steel reinforcement within the slabs. So, this type is economical and commonly used for highways and streets. Next is jointed reinforced concrete pavements or GRCP. So, GRCP includes steel reinforcement to help control cracks and reduce the number of joints required. So, the joints are spaced further apart compared to GPCP. So of course, no, it's ideal for areas with moderate to heavy traffic loads like airport runways or industrial roads. Next is we have continuously reinforced concrete pavement or CRCP. So this is actually the third type, no? So CRCP has continuous steel reinforcement throughout the concrete. So no contraction joints are needed. Cracks may form but they are tightly held together by the steel reinforcement. So this type is chosen for high traffic areas like expressways and highways because it offers long-term durability. And the last one is pre-stressed concrete pavements or PCP. So finally, no, PCP uses steel tendons to apply tension to the concrete, making it stronger and reducing cracking. So it's highly efficient, requiring thinner slabs compared to other types. So this PCP, no, it is a type that's used for areas that bear exceptionally high loads such as airfield runways. So inferior criteria of rigid pavements. So traditionally, fatigue cracking has been considered as the major or only criterion for rigid pavements design. So the allowable number of load repetitions to cause fatigue cracking depends on the stress ratio between flexural tensile stress and concrete modulus of rupture. Now here we have soil stabilization. So soil stabilization is the treatment of natural soil to improve its engineering properties. And next is we have chemical stabilization that usually involves the addition of 5 to 14% Portland cement by volume of the compacted mixture to the soil being stabilized. So the procedure of stabilizing soils with cement involves pulverizing the soil and mixing the required quantity of cement with the pulverized soil. Next is compacting the soil cement mixture. And the last one is curing the compacted layer. So we have also asphalt stabilization. So it is carried out to achieve one of or both of the following. So the following are waterproofing of natural materials through asphalt stabilization. So it is maintaining the water content at a required level of providing a membrane that impedes the penetration of water, thereby reducing the effect of any surface of water that may enter the soil when it is used as a base course. Next is we have binding of natural materials. So it improves the durability characteristics of the natural soil by providing an adhesive characteristics whereby the soil particles adhere to each other, increasing cohesion. And next is we have lime stabilization. So it is one of the oldest processes that improving the engineering properties of soils and can be used for stabilizing both base and sub-base materials. Now we have AASHTO design method. So the AASHTO method for design of highway pavements is based primarily on the results of the AASHTO road test that was conducted in Ottawa, Illinois. Next is we have design considerations. So the factor considered of the AASHTO procedure for the design of flexible pavement as presented in the 1993 guide are pavement performance, traffic, road soils or subgrade material, materials of construction, environment, drainage, and the last one is reliability.